A 125 gram sample of an unknown metal is heated to a temperature of 100 degrees Celsius. The metal is then added to a thermally insulated beaker containing 150 milliliters of water at 20 degrees Celsius. The final temperature of the metal-water mixture is found to be 25.7 degrees Celsius. Using this information and the list of specific heat values provided, determine the identity of the metal. So in this case, we have an unknown metal and we're adding it to water. So we need to identify what we're going to consider to be the system and what we're going to consider to be the surroundings. And in this case, since we have our metal and we have water, we can pick one of them to be the system and one of them to be the surroundings. In this case, I'll let the metal be the system, and I'll consider the water to be the surroundings. And we know that when we have a system and surroundings, we know that the heat of the system plus the heat of the surroundings has to add to be zero. So what that really means is an expression of conservation of energy. The heat lost by one has to equal the heat gained by the other, and so one of these will be positive, one of these will be negative, and when you add them together, you should get zero. So in this case, my system is going to be the metal, so let's call that QM for metal. And we'll call this one QW for water. And so that must equal 0. Or I can rewrite this and say that Q water has to equal the negative of Q metal. Okay, so the heat lost by one has to be equal to the heat gained by the other one. So now we know we have a formula to work with, and we know that heat can be written as the mass of the substance times the specific heat of the substance times the change in temperature. And that's the formula that we're going to use here. So let's use this expression right here, and let's use this expression right here. And so this will be Q for the water. Okay, so that's going to be the mass of the water times specific heat for the water times the change in temperature. Well, when we're adding the metal to the water, they're going to have the same final temperature. So I'll just call that final temperature T final. Remember, delta T, change in temperature, is always final temperature minus initial. Okay, and the water has a different initial temperature than the metal. So let's call this initial with a little W for water. And that's going to equal the negative of the mass of the metal times the specific heat of the metal times the final temperature minus the initial temperature. And again, the final temperature is the same, but the initial temperature, I need a little subscript M for the metal. Okay, so do I have all these variables here? And what am I solving for, actually? Well, I want to find the specific heat. I have these values of specific heat over here, and if I can find the specific heat of the metal, I can locate it on this chart and then figure out the identity of the metal. So that is the specific heat of the metal. That's what I'm trying to find. I have the mass of the metal, that's 125 grams. I have the final temperature, that's 25.7 degrees Celsius. I have the initial temperature of the metal, that would be the metal's heated to a temperature of 100 degrees Celsius. Final temperature, I said that I have. The initial temperature of the water I have, that's 20 degrees Celsius. And specific heat of water, I can look that up. The mass of the water. Well, I have the volume of the water, and I know that density is mass divided by volume. So mass is the same thing as density times volume. So the mass of the water I can write as the density of water times the volume of the water, and I can plug that into the formula. So I can just rewrite everything here that I have, and then what we're going to do is we're going to solve this formula for the specific heat of the metal. And then once we have our value for the specific heat of the metal, we can look it up on the chart and see what the metal is. So if I want to solve this for the specific heat of the metal, this is pretty easy to solve for. I'm just going to take this other stuff and divide it over to the other side. So I'm going to have a minus sign, so I'll put that out front, minus, and then the numerator is just going to be this stuff right here. So that's the density of water times the volume of the water times the specific heat of the water times the change in temperature, T final minus T initial for the water. And all of that is going to be divided by the mass of the metal times the change in temperature. And I think we're ready to plug in numbers. So let's see, I have the minus sign. The density of water. Well, the density of water, I'm going to use the value of 0.998. You can just look this up somewhere. This is density of water, and this is in grams per milliliter. Okay. Volume of water, they tell us we have 150 milliliters, so that goes here, 150 milliliters of water. And the specific heat of water, that's something else that you can look up, and that's 4.184. And the units are joules per grams times degrees Celsius. And now the change in temperature, the final temperature was 25.7 degrees Celsius. The initial temperature of the water was 20 degrees Celsius. And that is the numerator. Okay. So all of this is going to be divided by the mass of the metal. The mass of the metal was 125 grams. And we have the change in temperature. Okay, final temperature was 25.7 degrees Celsius, minus the initial temperature of the metal, that was 100 degrees Celsius. And if you notice, this is going to be a negative number. That's going to cancel with the negative that's out front here. All right, if you do all of this on the calculator and you're very careful to use parentheses here for the denominator, then you end up getting a value of 0.384. And that'll be in units of joules per grams times degrees Celsius. And so if we look at the chart up here, we see this looks the closest to 0.385. So the metal is probably copper.